Hello? There we go. Hello and welcome to United Astronomy Clubs of New Jersey. While I'm just going to let anyone who is still parking file in, find a seat uh, in time for the chat, I do want to welcome everyone here into our observatory here at Jenny Jump State Forest in Hope, New Jersey. And also welcome to everyone joining us online on both our YouTube and Twitch channels. Like I said, to give people a little bit of time to get down here, I do want to encourage everyone to check out our website, uacnj.org. It's gonna it's where you're gonna find a whole bunch about us as a nonprofit astronomy organization, as well as information on our upcoming talks, our past talks, and information on our member clubs because we're actually an astronomy club made up of other clubs. And one of the easiest ways to get into astronomy as a hobby is to join your local club, not only for ease of access, but also because they're going to have all those tips and tricks for observing that for are very relevant for your local area because the tips and tricks I know for out here in Warren County are not quite as helpful if you're coming from places like New York City or Scranton. Uh, do follow us on our social media pages. We have Facebook, Instagram, we have a Discord server, all great places to find out what we're up to. We'll post any upcoming special events that we may have. Uh, and they're also great places to get in contact with us, ask questions, or just share your own love of astronomy. Uh, there's normally a bit right here that I forget, so I'm going to move past that one and move on to the next. So for anyone joining us here, uh, I see someone going yay in the background here. Uh, but for anyone joining us here, we are inside, which is a little bit of a change up because we normally have the lectures outside, but since it is quite rainy and inclement outside, uh, on your way in, you pass the porta potty. It is big, it is blue, it is illuminated by a red light for ease of finding in the dark. When we go to leave, I do ask that we use our headlights just for the fact that we don't want to get run over, and that'll help us not do that. Uh, Also, as we're wandering around, if we're wandering around in the dark and need to use a flashlight or our cell phone light to make sure we're not tripping over our own feet, I do ask we keep those lights pointed towards the ground just so we don't have any additional chances of losing our night vision. It is inclement weather, so it's looking like we're not going to be able to open up a telescope, unfortunately, because we don't want to damage them in the heavy rains. That being said, on your way filing in, you did go through our little gift shop and museum area. Feel free to check that out. I will be manning that area after the talk because I still haven't been able to be allowed to be in two places at once yet. All right. Yep. Just find a seat. You are not here to listen to me blabber on for forever, though. You're actually here to learn about radio astronomy with Mark Sproul. Mark Sproul has a BS degree in computer engineering from Rutgers School of Engineering and a master's degree in mechanical engineering from Stevens Institute of Technology. He worked for the U.S. Army on embedded computer systems specializing in low-level image processing. And his interest in astronomy started in the early 1990s, writing software to read and display image data from NASA Voyager, Viking, and Magellan space probe missions. And with that, someone much smarter than me to talk about this topic, here's Mark.
SETI. That's not what radio astronomy is. So, what is light? Light is electromagnetic radiation. It's a particle, it's a wave, it has a frequency, it has wavelength, it has energy, and we can detect it. We know visible light. When we think of light and we think electromagnetic radiation, we think of what we can see with our eyes. The electromagnetic radiation spectrum is much larger than that, from gamma waves all the way to AM and everything in between, X-rays, infrared, or broadcast TVs, or what our cell phones use. Uh, they're all different frequencies. They're a very narrow band. They're in the middle. That is what we can see with our eyes, and that's what we traditionally think of using telescopes for. But it's all electromagnetic radiation, and we won't go into the quantum mechanics of how light works. That's a different lecture. This is a chart showing what the different wavelengths are used for. The lower frequency or longer wavelengths, radio, microwave, then we get infrared, or visible light, ultraviolet, X-rays, and gamma rays. If you remember nothing else, you should remember this slide. This slide is why we are alive. This slide shows the absorption of light, of radiation by our atmosphere. Gamma rays, X-rays, ultraviolet, all these are very bad for us. If we didn't have these blocked, we would be dead. So our atmosphere protects this. But we see that visible light comes through, a bunch of this other stuff, and then radio waves come through completely. So looking at this spectrum, this chart, what is the biggest area that we can see from the Earth, from ground into the sky? We can see radio waves. We can see light, obviously, and some other things, but we can see a great big whole bunch of radio waves. But this other stuff, the atmosphere protects us, so we cannot look at this from the ground, which is a good thing. Um, so many of you have probably seen the Crab Nebula. It's a very common thing, very common picture to see around. And if we look at the same thing, this is a visual image of it. If we look at the same thing, looking at radio waves, it looks like that. It's just light of a different color that our eyes don't see. We can think of it as light, as electromagnetic radiation. It really isn't light because our definition of light is what we can see with our eyes. And we look at the same image in multiple different radio waves, infrared, gamma rays, X-rays, ultraviolet, every different wavelength, it looks different. So there's different information there. Most of you have probably seen some variation of this picture of the Milky Way. And if we take the Milky Way and that same picture and we make it in a straight line, it kind of looks like that. So that's what the Milky Way looks spread out. So here it is in the top one is in radio. The second one is optical. That's what we're used to. Then gamma rays and neutrinos, and I don't know much about neutrinos. Just so we see different information. This is more detailed. The top one is radio at 408 megahertz. The next one is atomic hydrogen, which we'll be talking about later. Radio at 2.5 gigahertz, molecular hydrogen, infrared, different X-ray. Again, the different wavelengths, we can see different things. This is a map of the night sky at 408 megahertz. Now, when did radio astronomy start? A gentleman named Carl Jansky, born in 1905, was working for Bell Labs right here in New Jersey, not that far from here in northern New Jersey, because AT&T was doing radio transmission for doing telephone communications. And he was an engineer, and his assignment was to investigate static, because static was a problem that would interfere with conversations. So he was investigating the causes of static, and the causes, car ignition causes static. All kinds of things cause static. And he stumbled across the fact that there was static being generated from the sky. There was and he was able to pinpoint it at the center of Sagittarius, which we now know is the center of our galaxy. So he is considered the founding figure of radio astronomy. He's the one that discovered that radio waves were coming from space. And this is a picture of his contraption. It's made. You can see the black tires and scale. This was a rotating antenna array that he was able to move around to point his antenna and determine the direction of the radio signals. The astronomy professionals totally ignored it. Others said, "Oh, that's nice." They had no interest in it. They didn't care about it. Bell Labs was interested in telephone communications. They didn't want to do a lot of research and put in a lot of money into the study in space because they were trying to make money doing telephone communications. Now, we are a club of amateurs, and we're all amateurs, which is important about this gentleman, Grote Reber. He was a radio engineer, but he was also an amateur ham radio operator. That was his hobby, just like we are a hobby. I happen to be an amateur radio operator. I grew up around ham radio. My father was ham radio, so I had been doing around it my whole life. But he was an amateur radio operator, and he is the first radio astronomer. He built a radio telescope in his backyard, which was huge. Imagine doing that in your backyard. The picture on the left is the one he built. The picture on the right is a recreation of it, which is down in Green Bank, West Virginia. And Green Bank, West Virginia is open to the public, and you can go down and see it. But he built this, and he's considered the father of radio astronomy. Again, as an amateur, that he figured all this stuff out. Again, back to New Jersey, this radio tower is in Wall Township, and it is also open to the public. You have to go online. It's not open every day. I think it's Wednesdays and Sundays. But they have a program down there. You go down there, and one of the telescopes you can actually use and play with. I haven't been there yet, but that's on my to-do list. Green Bank, West Virginia is still active. A very large, I think it's a 100 meters across that dish. It's a huge dish. Still active down there. Again, that's not that far away from here down in West Virginia. And it is also open to the public. The most iconic and most well-known big radio dish is Arecibo. Unfortunately, Arecibo is no longer functioning, but Arecibo was made very popular in the James Bond movie GoldenEye, and in 2020 it collapsed. The towers supporting the middle section had not been maintained properly due to lack of funding, and one of them collapsed, and the whole thing fell down, and it would be hundreds of millions of dollars to restore it. But there are other large radio facilities current operation. Arecibo is now dead. There's the FAST one in China. The VLA and ALMA are great big. The VLA and ALMA are arrays. FAST is in China, which is bigger than Arecibo, but the same concept, which is a dish in the ground that doesn't move, and with towers supporting instruments over it. The VLA, or the Very Large Array, is also a very famous radio astronomy array. Probably the most common. I've been there several times, and it can be configured from very narrow to those dishes, which are huge, can be moved on railroad tracks and positioned to get high resolution versus high accuracy, depending on the science that they're trying to do. So the dishes are movable. This is actually a picture I took when I was down there. And who has seen the movie Contact with Jodie Foster? Anybody? If you haven't seen it, it's a good movie. It's science fiction, of course, but it portrays the VLA in the movie. ALMA is another big one. Again, there's a person on the ground for size comparison. Why are these dishes so much bigger? The wavelength of radio is several orders of magnitude larger than the wavelengths of light. Your mirror, because this is what these are. These are a parabolic mirror, just like in our telescopes. It's a parabolic mirror that reflects and concentrates those radio wave signals, those electromagnetic signals. But since the wavelength is so much bigger, that mirror has to be so much bigger. The thing that they can do with these arrays is they can add them together. They can take the signals from multiple ones and add them together mathematically to make it appear as if it was one or one mirror, this whatever the diameter of that array is. So VLA I think is 30 kilometers. So it's like the 27 dishes act like a dish that's 30 kilometers in diameter. Why I'm interested in is I'm interested in the math on how that works and the software that makes that work because it's very, very complicated. Now, what have we done with radio astronomy? Pulsars, hydrogen mapping, the cosmic wave background, black hole imaging, and quasars or fast radio. These are things that have been discovered that could only been discovered with radio astronomy. The point being, yes, there is some stuff out there that we didn't know about until people started observing with radio astronomy. So pulsars is a dead star spinning very, very fast. And when you're looking at it, it's spinning. Like think of a beacon of a lighthouse beacon. It turns and you get a flash. Well, these things, some of them spin at 100 times a second, and you're getting this pulse as the radio wave passes by the Earth. We see the pulse, and that's why they call it a pulsar. It's a collapsed star, spins rapidly, emits radio beams, it appears to pulse, and they were first discovered as little green men. This lady, Jocelyn Bell Burnell, they discovered these pulses and they thought it was aliens, and they labeled it little green men because they could not come up with at the time, had no idea what could be causing a pulse like that was natural, and later and that discovered to be pulsars. Another thing is the hydrogen map. So the top image is what we see of the night sky in visual, and then look at the same thing at the hydrogen emission. And we'll talk more about the hydrogen emission a little bit later. The cosmic microwave background is the leftover radiation from the Big Bang from 13 billion years ago. This color map represents a temperature range of only a few tenths of degrees Kelvin. But they were able to determine this using radio astronomy of this background of what happened at the Big Bang. Black holes. This image of a black hole was created using radio astronomy. It was using a big array of them spread across the world. Remember I said we could take these data from multiple dishes and add them together. Well, they did that using dishes not all in one location, but spread across the world. So basically we had a dish the size of the Earth to image, and this again, this is not what it would look like with your naked eye, because these radio waves are not something our eye sees. So we measure the intensity of it, then give it a false color so that we can see it in the image. And the telescope that was used is the Event Horizon telescope, and this is some of the dishes again down in Chile that were used to do that. Next thing we discovered was quasars. A quasar is kind of like a pulsar, but it's a galaxy that's generating energy from the galaxy as radio signals, very, very high power radio signals. First discovered as radio sources powered by galactic black holes. Sun produce more energy than the entire galaxies put together. What can we do as amateurs? I've said earlier that Grieber was the one that basically was the first real radio astronomer. He was an amateur. There is available for $350 a kit that allows you to look at the hydrogen line. This kit is designed for high schools to buy for a science project, but for $350 you can get one for yourself. Hook it up with a computer, and you can measure the intensity of hydrogen, which would allow you to map out the Milky Way. One thing to understand for those that are used to seeing all these fancy images that we have on the wall, and you see stuff from Hubble and James Webb, a single dish, think of it as a 1-pixel camera. Your cell phone has megapixels cameras, and this is a single dish acts as a 1 pixel camera. So it's not something you're going to go out and get and produce fabulous images with a single little dish. But you can map out the Milky Way and things like that. So this project is called Radio Jove, allows students and amateur scientists to look at the radio emissions of Jupiter and the Sun, uh, and play with it. And what you look at is something like this, which is what's called a waterfall display. Time is on the vertical scale, frequency is on the horizontal scale of the intensity of signals over time that's being emitted. And it takes a bunch of learning to understand how to read this, but it's something that is capable. A high school student can learn and play with. Another very good system is this website I think it's in Italy, where you can log on to say I want to download some data, to tell it when you want to take some information, and it will do it in what time frame, and what it's got a range of frequencies that you can specify, and it has a dish that will then take the data and email it to you and give you this data. The top image is a waterfall like before, and over time and a spectrum, but allows you free of charge. There's no sign up fee. You just, hey, I want to do this, give it your email address, it'll do it and send you the data. Obviously, you got to learn a fair amount about what to do with the data, but it's available for free. Now, I spoke several times about the hydrogen line. With the hydrogen line, an amateur can look at hydrogen and determine with Doppler shift. Doppler shift is when a ambulance is coming towards you, the frequency increases. That's called Doppler shift. That works in light as well. So we know the frequency of this hydrogen, which is 1.4 gigahertz, 1420 megahertz. And we can measure that, and if it's a variation of that, if it's a little bit greater or a little bit less than that 1420, that is either going away from us or towards us. So we can point our telescope, or our radio telescope, which is again a 1 pixel camera, at different locations and map out the variation of frequency, which should be 1420. Okay, it's a little bit more here, a little bit there, and map this out. And it takes a fair amount of readings and such, but as an amateur you can actually do the calculations of what is the rotation of our galaxy. With amateur equipment, that $350 kit, you could actually do stuff like that. When I first started in astronomy, and even 10 years ago, a radio receiver for doing radio astronomy was $10,000, and that was just the receiver. You still had to have the dish and everything else. Today we have software-defined radios, which are these little USB dongles that can be had for as cheap as $50, and a good one's $200, that does everything that $10,000 radio did 10 years ago. So for a dish and a couple of these little pieces of electronics for a few $100, you can get started with it. So mapping of the hydrogen line, which is what I want to do first. Again, I said it's a 1 pixel camera. This is looking at the intensity of hydrogen throughout the entire galaxy at a very, very low resolution. Remember, it's a 1 pixel camera, so you would set it up as the Earth rotates to scan, then the next day you would raise it up a bit and scan again, and over time you take all these scans, add them together, and you get a picture of what our Milky Way looks like. You can map out the Milky Way. Now, this I included because I think it's really friggin' interesting how this works. I said earlier about quantum mechanics that I wasn't going to be talking about quantum mechanics. I lied. I'm going to talk a little bit about quantum mechanics. So, hydrogen emits this 1420 megahertz signal, and it does it when the spin of an electron switches. So you got the spin, if you see the diagram, it's spinning up, and then the spin changes. It happens about once every 10 million years in an atom. So how can we measure this signal that only happens once every 10 million years? There is so much hydrogen out there that it is a constant signal that we can measure, because it's happening constantly, even though each atom only does it once every 10 million years. Pretty freaking amazing. So it emits, when that spin occurs, it emits a photon at this 1420 megahertz, the electromagnetic radiation. I call it a photon, but our eyes can't see it. It's just, again, it's a different frequency. So what I am working on, the picture on the left is right out behind here. If you look out that door, you'll see that picture on the left. That's a dish that's here, not currently being used, but was set up for using radio astronomy in the past. The picture on the right is my yard with, I've got two dishes. The dish in the back is currently half put together. And these are what I'm working on to do the hydrogen line stuff. And I want to do the measuring and mapping of the galaxy. And then what I want to do, I talked earlier about the arrays, the correlation. My interest is understanding the math for taking the multiple dishes and adding them together. And it's pretty, my background is I'm a computer engineer. I love writing software. And this is a very high intensity software application that I think would be fun to do. So you get a couple dishes and a couple of these software defined radios. In fact, there's one company that makes a software defined radio that's 5 software defined radios in one box, because you have to have the clocking the same. So that allows you to hook up 5 dishes. So if you've got one of these dishes in your yard and you want to, or nobody that's knows somebody that's got one that you want to get rid of, let me know and I'll come take it down. So, and you see them all over. You drive around, you see them because they used to be, nobody uses them anymore. They're not using it now. You got the little dishes for dish TV, but in the early days of satellite TV, this is what you had to have, an 8-foot or a 10-foot dish to be able to receive the signal. So there's quite a number of them around, and I've acquired a couple of them, and ultimately I want to get 5 and hook them all up with this 5-channel software-defined radio. There is a Society of Amateur Radio Astronomers. So it's not just, there is a really, or like we're a club here. There is it's actually a worldwide club that they have online meetings a couple times a month on Zoom that you can go into. So there's a lot of support out there. There's, like I said, the software defined radios are very, very cheap today. You need a dish, $50 low noise amplifier, some coax cable, the software defined radio, and a computer, and you're up and running. So for, like I said, that $350 as a kit, or if you wanted to build one yourself, by the time you build the feed horn and everything, you're looking at probably $500. But that's the cost of a typical telescope these days, so it's not, it's very affordable. Questions? Yes, sir.
All right.
Hi, Mark. I have, I think, if I can remember them, 3 questions. The first one uh, is when you were tying various dishes together in the same array, in the same local area, the same field, so to speak. Uh, is that also considered interferometry?
Yes, it is. It's interferometry, and the optical interferometry has to be done on an optical bench. Has to be the same location, but radio interferometry, if you have nanosecond accurate data with all the signals, it's called correlation. So you got 2 sine waves coming from 2 different sources. Now you got these 2 satellite dishes pointing at an angle to some point up there. Well, it's going to get to this one before it gets that one, so you have to time shift it, match all this time up, correlate them, and then you multiply the signals together to get. So yes, it is interferometry, but you can do it mathematically versus in optics, you have to do it optically.
Right, because I was familiar actually with the more planetary interferometries where they make planet-sized telescopes
Yeah.
with the very big research
Yeah.
telescopes.
So and it has been done by amateurs doing this sort of thing, and that's my ultimate goal.
The second question that I can easily remember, I'm having difficulty with the third, is the last slide there, or one of the last slides uh, with the club. Are there people who are? Is everyone highly technical in the
Oh,
field like you are, or are there what one might refer to as script kiddies who just run the software that
I
is
believe there's
developed?
both. There's a lot of very technical people, but there are some people. Like I say, you go down to Wall Township and just start playing with the stuff. Go in there on a Wednesday afternoon, and the website says you can go in there and bounce your voice off the moon.
Cool.
So
And
and with this system that's in Italy, that you can go online to, and in 2 minutes fill out the form, say without even knowing what you're doing, and then get the data back, and then spend some time learning what the data is. They've got tutorials and everything like that. So yeah, you can do it without spending a dime.
I did happen to remember the third. When I see some, obviously they're what look like low res images to us, but are very high res. I imagine in the radio astronomy field. But when you are able to resolve individual stars, what size array are we looking at, either mathematically or
The the the, v,
physically?
the VLA the VLA is the best example of that. Um, Back to
It
it.
starred in the movie Contact.
Exactly.
So if you're wondering about that, at least how it might look. I don't know. I haven't read that book.
I've seen the movie. Where are we at? Here someplace. So the VLA in its maximum configuration is 30 kilometers, yeah, in diameter. So that's pretty big. Uh, and what the correlation does is it takes, so there's 27 dishes. It takes every pair of dishes. So this dish to this one, this dish to that one, every combinatorial, I think it's like 300 different combinations that they come up with to do this correlation, and it gives them the pixel in the middle. I'll get there. Uh, so if you're spread out that so now you've got you know almost 400 pixels of an image, and for planetary work, 400 pixels is actually pretty big. And then you can then scan it over, do multiple images and mosaic them together. Uh,
I guess thrust of my question was, you need an array, or you need
well, the other thing that what I the first thing that you do is you get a dish and you're time sweeping it. You point it at 10 degrees and you record for 24 hours. And a 10-foot dish typically has a resolution of 5 degrees. So the next day you raise it up to 15 degrees and scan for 24 hours. And you go all the way up to about 80 degrees and you've now got 16 by 24 hours. So it's 16 pixels by say 320 pixels. So it's very low resolution. But you now have a map of the hydrogen intensity of the entire night sky, and that will then map directly to the outline of the Milky Way.
uh, right. One of our comments online, and I think this was right before you had mentioned some of them. Are there any places you know that you can go do things like radio astronomy and other citizen-based science without the outlay of money
Yes.
at first?
Wall Township, New Jersey, uh, has a, like I said, I'm pretty sure the website said they're open Wednesdays and Sundays, and you go down there and you can one of the dishes you can actually play with. Green Bank, West Virginia, is open to the public. The VLA in New Mexico is open to public, and twice a year they have open houses. I've been to the open house twice. Um, and they have a visitor center, so if you happen to be just driving down there, you don't have to wait to the open house. You can just stop in and see the place. Green Bank, West Virginia, is unique in that it is a radio-free zone. They only recently, like in the last 2 years, finally allowed Wi-Fi in the schools there. You can't use cell phones in the area. They don't have cell towers, and on the property, you're not even allowed to use anything but diesel engines because uh, uh, car ignitions generate too much static. They might have reduced some of those restrictions, but I know that's the way it used to be within the county. So the entire county down there is, you move there, you have to sign these things that you cannot do these things but it's been protected that way for as long as radio astronomy's been around. So people know that yeah, if you're going to move here, you've got these restrictions, and
Yeah, it's not like, hey, I'm going to move next to a farm. Shocked face when there are farm animal noises and smells.
uh,
um,
it's like light pollution. You gotta keep the radio pollution down.
all right. Was there another question out here? Paul again.
I just wanted to mention, because it ties into one of the presentations that I do, that you had mentioned the cosmic microwave background, and that was actually a discovery made when Bell Labs was actually commissioning, if not the first, one of the first radio telescopes.
So here's a picture of the VLA. You can see how far out it goes. These railroad tracks. And it's really pretty. These things are 30 meters across and weigh like 450 tons, and they can pick them up and move them.
Anything can be picked up and moved if you have the right rigging. All right. Our next online question is, what kind of equipment do you need to hear the moment when Jupiter rises above the horizon?
That's the Radio Jove, the $350 set called Radio Jove that you can buy. That's exactly what it's for.
That's more money than I want to spend, unfortunately.
You can build it yourself probably for $150 because you got the software defined radio and the LNA. Those are $50 a piece, and you get an old. You probably could do it with like an old dish TV dish that's not being used.
Yeah, I think if this person who asked the question is who I think it is, I believe it's a person who drove his car down the road with one of those dishes as a hat. By the way, it's hilarious when you see one of the old radio TV dishes over one of these small compact sedans driving down the road. It's actually quite comical. Also, if you do that and you wear it as a hat, you need to make sure that you haven't strapped the dish where the doors can't open and you can't get into the car. So trailer might be the best way to.
You know this from experience?
No, I definitely don't know that from experience. Yes, I do. But also back to the person asking other citizen-based science. Honestly, Google's going to be your friend. Find your local astronomy clubs. Chances are there's someone who's into radio astronomy and they'll have those local resources. We have a number of science-based streamers on Twitch besides us. I believe Nerdwino the other day was actually, they were learning about exoplanets and how they were identifying exoplanets by looking at light variation in a star. So go find your science-based streamers. Go talk to
Here's my
your college friends.
Here's my email address if anybody wants to reach out to me.
Your library. all great places to start looking for uh, that sort of information. All right. Any other questions?
Yes. Yeah. Yes.
Yes. Paul in the back has pointed out that Mark is currently helping running the Northwest Jersey Amateur Astronomer Club based out of Blairstown, New Jersey, and excellent resource for knowledge about astronomy.
And no
A
dues.
local
There's no dues. And
free.
we meet about what is it, 5 miles, 10 miles from here?
I
Oh,
don't know. It's
it's not very.
less than 30 minutes, therefore it's not even on my radio.
It's like 10 minutes from here is where we meet in Blairstown. Typically on Friday evenings, typically the first or second Friday. I don't remember the date of our next one, but NWJAA is the name of .org. You can look and find the website, and we have small meetings about this number of people in Alan's basement, and have lectures similar to this. Typically, our lectures are a little bit more technical in nature. Uh, uh, but that's a local club that's right near here.
And don't worry about it being technical. Uh, usually the people who speak are very much willing to explain things to you, and I know this from experience because I am only a little baby astronomer who does not understand some of the big words, and when the acronyms start flying, sometimes I do in fact need that help.
For those people that came in late, I want to emphasize about what is light. Light is electromagnetic radiation, and this is a chart. The visible light that we can see is only a very small portion of the electromagnetic radiation spectrum, and radio waves are just another part of that spectrum that we can use radio systems to detect, because things out there emit electromagnetic radiation in all different kinds of gamma rays, X-rays. We have I think it's out of commission now, but the Chandra satellite in space was up there for many years doing X-ray observing, because X-rays don't penetrate our atmosphere, so you can't look at anything in the X-ray band from the ground. You have to do it in space. Uh, so, and that's a good thing, because X-rays would kill us. If X-rays uh, came through our atmosphere, and gamma rays, which they're out there, but our atmosphere stops those. So if we want to look at those, we have to go into space to do that. And the Chandra spacecraft, I read a book a few years ago about the Chandra. It was named after an Indian guy, astronomer, who specialized in X-ray stuff. It was a really good book, really good. Because it was X-ray, didn't get much publicity, but it was a really good program.
There are hundreds of books and nowhere near enough time to read all of them.
I have most of them.
You're trying very hard to read all of them.
I've read over 20 history books in astronomy.
That's more than I have. All right. Since it looks like we're done with questions, I do want to thank everyone who's joined us here. Since I know a couple people snuck in after the safety briefing, if you need to use the restroom, that is the porta potty outside. It is big, it is blue, it is illuminated by red for ease of finding in the dark. It is in fact dark since it's a state park, and it is very cloudy, rainy, and poor visibility for any sort of astronomy except radio astronomy. We don't currently have a working radio dish.
What is there's a radio display over there on
So we do have in our little museum and gift shop area a display of, and that has the ham radio, ham psi. I need to remember that. I'm like, we're talking about radios. That's ham psi. Ham radio's a thing. It got smushed together. Ham psi put together a joint project with a bunch of different colleges and scientific organizations, doing some really interesting things that I don't understand. I could understand them if I spent the time. I have not spent the time yet. So do check that out because it has one of the waterfall display type things that Mark mentioned. Uh, Mark can probably explain many of the things on that to you.
It's measuring the ionosphere, the balance of the ionosphere, which is very important in ham radio and radio communications. And the ham sci project is watching the ionosphere propagation.
All right. Um, when we go and wander out into the dark, any flashlights, I do ask we keep them pointed towards the ground so we don't accidentally blind people. However, we are using our headlights because getting run over is no fun. I've also done that. Wouldn't suggest it. Let's avoid it. No one needs those medical bills. Um, that being said, thank you all not only joining us here, but like I said, online. We do live stream these to Twitch and YouTube. So do hit those like, follow, subscribe, the free actions. If you're feeling extra generous, you can do the paid action. But that's never expected, but always appreciated. And with that, until next time, clearer skies than tonight and good seeing.